Well, first, thank Alan to invite me to actually speak on topics which I'm not so familiar with, and but seismic anisotropy is a very broad topic. So, and in general, there's two ways to measure seismic anisotropy: body wave, surface wave. And surface wave is actually, you need tons of equation to do that. So I'm going to do the simple one, the splitting of the body wave, try to determine the distribution of seismic anisotropy at various locations and various depths. You know, and all this, actually, this is the citation of a wonderful paper, a pioneer work by Silver and Chan in 1991, and you can see they got like 600 citations, and the average, this is almost 20 years and 30 pages publications. And I would ask you to interpret these variations. You have a good means, but some variations. Especially you have a low in 1997. What happened? You become the chair? No, I don't think. So maybe, okay. So probably, I think, budget cut. Let's blame it, budget cut.
That was when the Republicans took control of Congress.
Or Clinton got in trouble, right? Yeah. Okay. Okay, so the part of the reason I was asked, to do this anisotropy because I worked with Paul, which is unfortunately had a tragic accident 2 years ago. But what I learned with Paul is not try to measure the seismic anisotropy, but another much fundamental or basic techniques for seismologists, which is a dig a hole. It's based on one thing is very important, and it's not everybody can do that well. And when I took the picture, I didn't put the hole there because Paul is not so good at digging. But anyway, so what I'm going to do actually is try to introduce the basically the seismic anisotropy, how to use the body wave using splitting to measure that, and give one example, which the only example I actually used the SKS to mapping the orogenic deformations beneath the Venezuela Andes. And then my interest is seismology, the point of view is whether you can constrain the source region that cause the SKS splittings, the depth ranges. So I will use a variety of phases to do that. And another thing is actually we know that all the seismic stations are basically deployed on the land. So whether we can do anything in the seafloor to measure the Tobias, the gigantic flows, right? That's another thing. And finally, actually, one thing I'm doing right now is try to see actually how much contribution from the crustal, especially like the crustal in Tibet, in the SKS splittings. So, well, the Earth, first we know actually the Earth is an isotropic medium. That's I really think. So, from this should be microscopic point of view. Is first is the mineral crystal are highly anisotropic, right? If you send in waves in different directions, you will get different velocities, and also in the top, like 10 to 15 kilometer, the crust, they have a variety of cracks and intrusions, and then when under a certain stress field, those structures tend to orient themselves to a preferred directions, which gives the seismic anisotropies. If you go actually a little bit details, is the stress field first, for example, the upper crust anisotropy is believed to be caused by the orientation of the cracks because the stress tended to close cracks in certain directions, open cracks in other directions generate some sort of seismic anisotropies. And in the Mantle, and I think Greg gave a very good tutorial lecture yesterday, and the deformations, the two types of deformations, and then can cause alignment of the crystals and then generate seismic anisotropies. So test yesterday, right? We had two types of the deformation mechanism. There are two types of deformations: diffusion creep and dislocation creep, and only one of them can cause seismic anisotropy. And this is the lecture note of Jennifer. So she didn't put anything there. So I will ask seismologists which is diffusion creep and which is the dislocation creep. Which one can cause seismic anisotropy and which one cannot? Is that a volunteer?
The left one is diffusion.
Huh?
The right one is dislocation.
This one?
Diffusion.
Diffusion. Is this a diffusion? Raise your hand. I have an injury. I cannot raise my right hand. Is this dislocation?
Diffusion. One on the right is super fast.
So you see which one? Then let's ask that. Which one can cause seismic anisotropy? The left one, right? So dislocation. Right? So, this is Sally's lecture. Note, it's much better, right? So is this one? This one is.
Actually, you have my notes overimposed.
Okay. So grains tend to stay in the same shape, but pass around each other, so they will stay the same shape. So there's no actual dilectivity.
The lecture notes from some lecture I gave at Rice, I think.
Yeah, that's.
They are.
And the thing on the right, I didn't tell you guys this, but during diffusion creep, most of the strain is actually accommodated by the grains moving past each other.
So
you can see there's the two little spots in the right-hand grain.
This one.
You can see that grain hasn't deformed at all.
So which is not showing in Jennifer's.
Yeah.
Right?
And so that's
showing there too.
Diffusion creep, and then the one where the grains get squished, you can see the spots are moving close to each other.
Yes,
And that's
the
because
points
the
are
grain
there.
is internally deforming, and that's dislocation.
Yeah, so now it's clear, right? Only this one, dislocation creep can cause seismic anisotropy, and then there are certain depths. There's a transition from dislocation to diffusion. Okay, so now we are doing the seismology part. So basically, seismic, the velocity is so the seismic velocity reflects the elasticity of a material, right? So it's and we know in the extreme most general case you can have 21 elastic constant. So in this kind of case, so the seismic velocity will be a function not only the propagation directions, and we're also on the polarization directions. If you move like this and or like this, they will get different velocities. Now try to get a simple. Now in an isotropic media, we can actually decompose the wave field into the P waves, the compressional waves, which have a polarization direction parallel to the propagation directions, and we have two shear waves which have the polarization direction, the motions perpendicular to the propagation directions. And in weak anisotropic medias, and we have two cozy S waves which have the polarizations actually also roughly perpendicular to the propagation directions, but this time they have different travel speed. Right? One goes fast, another travels slow, and the P wave have a slightly different polarization direction with the case in an isotropic medias. Now, when we quantified anisotropy, we basically take the difference, divide the average, so that basically the difference between the fast and the slow directions, and divided by average. And usually it's in percentage, like in 1%, 5%, this kind of numbers. So when shear waves propagate through an anisotropic media, at the beginning, it's basically a displacement vectors you can project into any kind of orthogonal directions, and you can project in the fast direction, which shows blue, and the red directions is the slow direction. Then the two waves, the two vectors, displacement vectors, will have different velocities to propagate through this anisotropic media, resulting in a separation of the two wave field. And basically what we measure is the direction of the blue direction, the vector direction, fast directions, and the strength of the anisotropy is defined by the delay times, the time between the fast and the slow direction. And you can do, if we assume the length is the L, in this case, the wave travels almost along straight lines, L divide the time of the slow waves and subtract the fast travel times you get, and you can see actually the delay time is proportional to the degree of anisotropies. And so basically, in principle, you can use this method and using a variety of waves to map out the 3D variations of seismic anisotropy in the mantle and the crust and the cores. And I did some work in the cores, but I will not mention it here. And in general, there's two types of seismic anisotropy. One is called a radial anisotropy, which have the symmetric axis is kind of lies in the vertical or the radial directions. And in this case, you can see even a layered media. You can see actually can generate those kind of radial anisotropy. If you think, if you have a book and if you deformed in different directions, you will get the you will get a different. I think in certain direction you cannot easily deform it, but in certain direction it's very easy. So, and this is usually is usually mentioned in the surface wave anisotropies. Basically, surface wave is a horizontally propagating waves, and this media have basically symmetric axis is a vertical, and in this case, love wave, the velocity you determine from the Rayleigh wave and the love wave are different, and this actually related not only the anisotropy, and another aspect is the layering. And another way actually looking at the radial anisotropy is the body wave, the deflector shear waves at the core mantle boundary. And so basically a deflected wave is S wave which stay along the core mantle boundary for a while and then will go back. And you can see which the SH waves have a propagation direction is horizontal polarization directions, and near the core mantle boundary, SV will be vertical polarization directions. You will imagine that there's the difference in propagation velocities. So shown here is examples of the recorded SV wave, deflected wave, and SH deflected waves. And in this case, you always find the SH wave leads by a few seconds. Now, there's a variety of places which can cause this difference in travel times, but you can using a variety type of other kind of waves to constrain that the source of the splitting is near the core mantle boundaries. For example, you can use the reflected at the core mantle boundary, and sometimes in some space you can see the reflected waves at the top of the D double prime layer, so-called D double prime discontinuities. And if you measure the splittings of different waves, then you can find out which is the place caused the observed seismic anisotropy. So I will not go the deeper part, this kind of seismic anisotropy. What I will focus on today is the azimuthal anisotropy, which have a symmetric axis lies in the horizontal plane, which in basically, if you have a vertical propagating waves, then depends on the polarization directions, then you will get a different travel velocity. We go back this figure again. If we actually write the equation in a different ways, basically this is, as I said, the wave, basically the displacement is the vectors. And if you go from isotropic medias, if you have a source wavelet, basically you have a phase shift, but the propagation, the vector will stay in the same directions if you go through an isotropic medias, right? So if it goes through isotropic medias, so the vector will stay in the gray shaded plane. But if for a splitting for an anisotropic medias, then the vectors, the direction will be rotated, and actually you will not get linear the vectors. You will give displacement. Actually, it has elliptical particle motions. This is because the fast motion and the slow displacement are not in phase. So basically, what you can do is actually time is so-called splitting operators, which you can think is a matrix, right? If you do the coordinate transform, you rotate a vector from one to another vectors. Simply you do is multiply the vector by a matrix. And this is the fast direction matrix, which you shift at the same time. You slightly shift this. You slightly shift the phase to compensate the difference in travel time, and this is basically the same matrix for the slow directions. And what you really do is basically a matrix operations, the multiple of the original vector by the splitting matrix. And now, when the original, the vector, p vector, if it's known, the equation can be simplified to which is to a much simplified forms. Consider a case like SKS, right? We use SKS. Almost most of the splitting are measured by the core phase SKS, which actually travels, go out from the source as a S wave and convert the P waves in the outer core, and then convert back to S wave again. So the motion should be longitudinal, and that's what it means. It should be staying in the plane, which contain the source and the receivers. So the S wave converted from the P wave will only have the SV particle motions. So we know the vector in this case, and so we apply the fast and slow directions, and we get actually a very much simple forms. For example, this is the R direction, which is radial direction in this case, in this directions, and is the faster direction is about an angle, let's say 5 from the fast radial directions. So since when the wave converted from the P wave from at the core mantle boundary, the particle motion or the polarization direction is this direction. This is the vector, displacement vector. You can project into the fast and the slow direction and got this fast and the slow direction. So that time you don't, and then the faster direction and the slow direction has different travel speed, and then you actually rotate them back to the radial and the transverse directions. So if there's no seismic anisotropy, the transverse, you will have no energy in the transverse component. So it means if delta T is 0, you will get 0, these terms. But since if you have a splittings, basically you will have these two terms cannot cancel each other, so you will have some energy in the transverse component. And so what's really interesting, and you can use it as a diagnostic, whether this, what you see in the energy in the transverse component is due to seismic anisotropy or other kind of scattering or reflections, is whether this actually the T component is the derivative of the R component. I will show you an example. In this case, the synthetic is actually calculate for receiver functions, which is another P to S conversion phase at the MOHO from the P wave to SD waves. So this is anisotropic media with 5%, I think, anisotropy. What you will see, this is the seismogram is plotted along the back azimuths. Okay, so you can see because you have seismic anisotropy, so different directions, waves coming from different back azimuths to the station will arrive at different times. You can see clearly there's cosine 2 phi changes. In other words, there you have values with a period of pi's. And then this is the transverse component. You don't see actual nice variations in travel time, but you will see a very nice change in the polarity of the waveform. So this is basically, if you take the derivative of this waveform, what you get is this waveform. Right? The first one is positive. Actually, this is kind of reversed. Positive half a cycle, and then you get the negative half cycle. So if you can use this relationship to see whether the observed energy in the transverse component is caused by seismic anisotropy or is caused by other type of structures like scattering and reflection from dipping layers. Is there any questions? So it's so simple, so everybody can easily find. So I will give, this is examples of the SKS waveform recorded in the radial directions, and this is in the transverse directions. And as I said, if you don't have anisotropy, you will have no energy in the SKS time windows. But if you do have, then that indicate either is due to seismic anisotropy or other type of structures. But in this case, you can pretty sure this is due to seismic anisotropy because you see actually the waveform is almost derivative of the radial waveforms. So what we do is we assuming the different fast directions and the different delay times, and then basically collect this and rotating back to rotating them to the fast and the slow directions. So if you assume basically if you have if you assume phi and if you assume phi, so you can project this radial to the fast and the slow directions. This is the first step. If you assume a fast direction, you can project them, and then you can slide each other's, because the fast direction and the slow direction, they should have a different arrivals. Then you slide try to, some case is try to take the cross correlation actual. When the cross correlation reach the peak, that's you can determine the amount of sliding. And or if you want to say it more fancy, you can compute the covariance matrix, calculate the eigenvalues, and for a linear polarization, you only have one eigenvectors, and so what you do is minimize the second eigenvalues, the minor eigenvalues. And once you collected this collected this splitting time, and you return back to the radial and the transverse directions, you will get negligible energy in this transverse component. That means what your collection is correct. So you can plot the energy, or in this case, I don't know what is plotting here, but you will see a peak or a trough or peak that indicate this is the horizontal, the vertical axis is the faster direction, and amount of delay time is the sliding time. You although it's pretty simple, but it's actually there's a lot. So people, if you choose different time windows, okay, and if you using either minimize the energy or maximize the close correlations, or even the ways to calculate close correlations, you will always get some slightly difference. And especially the problem here is it's very easy to find a peak, right? But the peak is not necessarily the right answers, because any point in this two-dimensional domain, if after you do the corrections, the energy in the transverse component is similar to the noise level, then in theoretical speaking, all these points could be solutions. So the minimum point or maximum point is not necessarily the best solutions. So this actually caused a lot of ambiguities and a lot of uncertainty in measure the splitting times. Sometimes you can get a different result. And I think the most, measure this, the seismic anisotropy, although there's still some sort of uncertainty error there, but the big uncertainty is how to interpret the seismic anisotropy. Right? This is the figure from Paul's review paper, and you can see there's two end member explanations. One, you can basically attribute all the observed deformation to the lithosphere. Another is to the asthenosphere, right? And this is, I thought maybe you know much better than me. This is Paul Silver's point of view, and this is kind of Vinnick's point of view. And in a lot of cases, actually, probably a lot of cases is between two of them. And in this case, you already assumed the SKS basically travels as an S wave from core mantle boundary to the surface. And this is, if you add the lithosphere, asthenosphere, is only about, let's say, 200 or 300 kilometers. So you assume all the anisotropy you observed is caused by the top 200 or 300 kilometers, because due to maybe the transition from this location to diffusion creep, then for this location, this diffusion creep, you're not supposed to have seismic anisotropies. So I have never did anything with using SKS splitting to measure the deformation. So what I really did is a very recent. I think this is done by Jennifer, and using the Bolivar data set collected a few years ago, and the studied area is the western Venezuela, and we know this Caribbean plate is moving relative to South America, 2 centimeters per year to the east, or you can say the Caribbean plate is not moving, the South American is moving west at a rate of 2 centimeters per year. And you have the Caribbean is subducting beneath the western Venezuela, and you have the Nazca plate is subducting beneath Colombia, and you have the collision of the Panama to the South America, so create a compressional domain in the northwest, the corner of the South America. And so what happened is the so-called Maracaibo block, which is defined by this strike slip faults, is trying to escape from the South America. And so in this area, you see a variety type of deformations. So you see those very high mountains is kind of localized deformations. In the same area, you also see like the Maracaibo block, which I'm not sure how much deformation you can see from the surface, but the northeast corner of the block is the Falcon area. You have see kind of a few 100-meter topographies, and those shown here are the fault. So we try to measure the seismic anisotropy, which is reflected the deformations in the mantle, lithosphere, or asthenosphere, try to understand what is the cause for this variety type of deformations. So the earthquake we used actually comes from 3 directions, and as you know, they are almost perpendicular to each other, which is actually not good to try to distinguish whether there is one vertically coherent deformations, or you have deformations changes with depths. But that's all we have. So we have to use them to measure that. And one stations, this is shown as we have, I think, 9 earthquakes. And shown here is an example of the recorded uncorrected SKS waveforms, and you really see a very large pulse in the transverse component, and I think it's probably real because it's the derivative relationship. So, and actually, I got one review told me this is probably not true because the frequency field is different. And I said, you know, if you take the derivatives, you tend to have a high frequency. So, and what you get from this earthquake is the splitting time. You have relatively the same fast direction, which in this case is almost east, west, and you will have very high delay times. And we changed the pulse method slightly, and when we define the error, we basically the error uncertainty is defined based on the noise level. If you have a larger noise level, basically anything energy after you collection the transverse component energy below to the noise level is considered as a possible solutions. So what we try to do is try to see whether all the solutions from individual earthquakes were actually overlaps. If there are overlap, that's basically give you a perfect solution. So this is the stacked solution of the faster direction and delay time. And this is kind of 3.2 seconds, which is probably one of the biggest splitting time that have been observed in the Earth's surface. Usually the splitting time from the SKS is around 1 second, right? And so this is the measured splitting time plotted in the map, and the bar indicate the faster directions, and the size of the circle is basically indicate this the strength of the anisotropy splitting time. And we can see actually it's nicely the measured anisotropy can be divided into 3 zones. It's the zones near the north coast, the north coast of the Venezuela, and all the faster direction is east to west. And the splitting time, average splitting time is near 2.5 and 3 seconds, which indicate whether there's strong east-west shear in this area, and the north to the, I think there's a Oka Fort, right? There's a,
You can see it. You see that triangular thing?
oh, this one, there's a photo goes through the.
If you just follow the top of the triangle, that's a big strike slope fault system.
Yeah. So this is the block, the 2 strike slip earthquakes. Hmm? Yeah.
One's right lateral, the other one's left lateral.
Yeah. So, and the other area is that you see actual very minor splittings below 1 second is in basically in the South America. So the direction is parallel to the plate motions, and between the two, we got the moderate 1.5, 1 to 1.5, or even to 2 actually second splitting from the station that situate on the Venezuela Andes. And when we write this paper, we argued that most of the anisotropy comes from the lithosphere. It's not for crust. And the crust here is about 50 to 55 kilometers, I think. So, and I'm not sure how actually. So probably some of the splitting is contribute from the crust. But we interpret this as basically this is the maximum extension direction. So basically it's so the dislocation deformations, and so which actually we interpret this is actually mainly in the lithosphere. So, this we need other kind of data actually try to basically to put in them into different, whether they are lithosphere or asthenosphere, but it's very hard to do that. So the interpretation is kind of qualitative, and what our interpretation for the stations in the coast is a kind of a strong flows that beneath the Caribbeans, and that flow may related to the larger scale flows in the South American continent proposed by Russell and Silver 15 or 16 years ago, and that's because the slab Pacific, because of the Nazca plate is retreating, and so you have the flows try to escape from the plate, and that's actually create a flow goes to the north and the south, and one branch goes to beneath the Caribbean, another is the what's the name? Scotia plate. So, and this one, and we based on some tomography images, actually this flows. The Caribbean plate, there's a tail or some sort of distortion here, and so was guided by this subducting Caribbean plate and create a very strong shear near the coast, which caused this really 3-second seismic anisotropy here. And for the splitting observed in the Andes, we think is mainly due to the lithosphere, and this is probably a pre-existing weak zones, and you can some of the evidence of these grabens in the top, and you can when get compressed, and these weak zones get actually deformed, and the lithosphere is thickening, and so now actually that's preliminary data suggests that lithosphere here is almost is almost similar to the surrounding areas. So that's kind of we interpret as a pre-existing zones and under compressions, and so that's kind of thing people usually do when they interpreted SKS splittings. You need to assume which depths actually is caused this SKS splittings. But from seismological point of view, you actually can use variety of type of seismic waves to locate actually where the sources for the splittings. For example, this is the work done actually in the early 90s, and you can, using deep earthquake or intermediate depth earthquake, you can compare the local S waves and SKS splitting times and to see whether they are consistent. If they are agree with each other, then you can be sure that much of the anisotropy observed from the SKS is from the shallow part beneath the stations. And another thing is you can using the SC almost vertically reflected SCS waves. So it's not showing here earthquakes reflected at the core mantle boundary and it comes back. And if these two are also if it's consistent with S waves, then it's another indication that the source for the seismic anisotropy is in the shallow part of the mantles. And you can, this example, the study done in Japan, and they find actually the discrepancy is quite small. But when you're using the reflected SCS waves, actually things is quite complicated. And this is probably only good for seismologists to apply these techniques. I understand there's a lot of people, non-seismologists, can measure the SKS splittings, but for SS, SCS, SS, it's not easy to do that. And I also actually has a doubt whether you can make this assumption why the SKS is, the splitting is caused by upper mantles. And actually this is the work I done that we try to use SKS compare and basically P660S, another converted phase at the 660s, the boundary between upper and low mantles, and we find stations in China HIA that you can see actually the P2S converging at the 660 very clearly, and the earthquake are from the deep earthquake in Tonga. And you can see, compare the ray paths. This shows the ray paths. They actually, the P660S and SKS, have exactly the same ray paths, S-wave ray paths in the mantle, but one travels as P-wave in the lower mantle, one travels as S-wave in the lower mantle. So by using this, you can actually separate the contributions from the lower and upper mantle. And we did this, actually, SKS is average is about 0.6 second, and from the P660S is 0.3 second. So there's some difference, and amazingly the faster direction is kind of similar. You have more or less the similar faster directions, and this shows a couple examples of the individual P660S waveform and the SKS waveforms. And so there's some suggestion that actually that there's some sort of anisotropy, azimuthal anisotropy in the low mantle, but the amplitude is really is not so much. It's 0.3 second, and this rate pass is almost, let's say, 2,500, right? So even if you divide by 5 kilometers per second, you will get actually the travel time in the low mantle is 500 a second. So this is 0.3 divided by 500 seconds is less than 0.1%. So it's really almost nothing. And I still try to do something more about whether really you can try to see whether there's other place that you have significant anisotropy in the low mantle. And the way I try to do that is try to compare the SKS and SKKS. So I shown here is the SK waves, so S wave, P wave, and KS. And another SKKS is the one-time reflection at the core mantle boundaries, and it's converted to S wave again in the mantles. And as you can see, they share a very similar rate pass in the upper mantle, but they are slightly different in the lower mantles. And this is another pairs in a different distance. And again, even at that great distance, the upper mantle or the upper mantle 200 kilometers, they have very similar rate pass. And I looked at a total of 76 stations, and I found only 8 stations shows some difference between the splitting, between the different splittings between these two phases. Okay, so shown here is an examples, and this is SKS. You have a very strong anisotropy, but SKKS you don't have that, and it looks like most of this exit point from the core mantle boundary is in near the Pacific Rim. So this is so a lot of people try a variety of waves, try to actually constrain the distribution of the seismic anisotropy, and this is a figure from a review paper of Savage, and what really with the distribution of the anisotropy, actually, the total SKS splitting could be to 3 seconds, and mostly the source region is in the upper mantles. And the cluster anisotropy are believed to be very small, less than 0.3 seconds or 0.2 seconds. And in the transition zone, there are some studies suggest transition zone have some sort of anisotropy, but I think that's mostly is the radio seismic anisotropy, because the waves, the deep earthquake they used is actually the waves SV actually has a vertical polarizations. And in the low mantle, I have some example showing it's really not so much. So we are kind of it's kind of sure that actually most of the seismic anisotropy as observed from SKS is either caused in the lithosphere or asthenosphere, right? So this, but this is a figure from a review paper by Matt Fauch and Stephanie, and they actually show the distribution of the azimuthal anisotropy and radial anisotropies beneath the different continent, and you see actually there are larger variations between the different continents. And in eastern North America and Australia, it seems the depths of the seismic anisotropy can extend to as much as 300 kilometers, and this can be explained the depths of the transition from dislocation to diffusion. Is different, maybe due to the temperature or other effect. But anyway, I think I don't want to go too much detail for this, but so when you have what we actually most case when we measured SKS, we kind of assume one layer of the anisotropies, then what which with the measured faster direction and the splitting time will be independent from the waves coming from. But if you have a more complicated anisotropy distributed beneath the stations, one example is beneath Berkeley's, the splitting time and the faster direction seems to change with the back asymptotes the wave comes from. So this is the circles. So this, and you can approach these issues using basically using the splitting operator method, and you can basically two metrics multiples, and it's not commute. That's something sometimes makes things difficult. And you can, written is as apparent splitting parameters, and this apparent faster direction and apparent splitting time can be determined using the regular method. But okay, so this I don't want to go too deep. So as I said, what really SKS is a very nice waves, has high signal to noise ratio, and you can really get pretty robust measurement of the seismic anisotropy beneath the stations. So what about the beneath oceans? We know surface wave can do that, but can we do it with other type of body waves? So I have been trying this, but it turns out very difficult. So as I said, other type of waves, you can use the SCS, and you can using like S refracted waves at the surface. You can using PS waves, a variety of waves. And what I'm going to show is I try to use this SS waves to image the anisotropy beneath the oceans and the earthquake. So this is actually basically this is why we needed to use that. And okay, this is quite a long time ago. And so even with that time, 10 years ago, with the global seismic network, you can have pretty good coverage at the seafloors. So what we try to use is try to measure the splitting, the anisotropy beneath this reflection point. And you have to use waves that have an incident angle less than 35 degrees to prevent the contamination from the other waves. But even with this, actually, you will see some problem if you're using reflection waves. So this is the study first done by Cecily and Paul in 1998. And this is, I think, earthquakes. This is, I think, the Banjo in South America, and probably some earthquake in Tonga or Indonesia. And shown here are the dashed line. You cannot see clear. Dashed line is the R component of the SS, and the solid line is the SH component. What you find is the SH component always lead the radial component by 10 to 20 second. And there's a polarity issues too. And I also try to look at, for example, one example of the reflection beneath the Indian Oceans, and you can see the same thing. So this, at the beginning, some people even try to use this data to measure the splitting anisotropy beneath the reflection point. But if you simply compare the result from the, if you assume that is the splitting, and SH is, if you have earthquake come from here to South America, so the SH wave, the faster direction is like this. And the reflection point is near the East Pacific rise. And they have the melt experiment, and you can measure the splitting as the SKS, which basically perpendicular to the ridge axis and very nice. So this is definitely not correct, right? So the same place. So what I found is actually when you have a reflections, things become much more complicated, especially at the surface. Now this is, I did a very simple calculation of actually how, so what kind of waves will generate during the reflections. So you would assume that dashed line is the SS reflections, and which is the main pulse, and from the radial and the transverse component. If they are isotropic, they should arrive at the same time. But beyond this, the main pulse, you also have kind of conversions. Let's say in the radial component, you have S to P conversion, then converted S wave back, and then different. So that arrives earlier than the main pulse, and it's quite big. And you also have the reflections from the oceanic moho. And this, I think I computed with a moho depth of 10 kilometers. And you also have those reverberations. And this, you see the time scale, the separation of this phase is only like 4 or 5 seconds. And now if with the high frequency data, we have no problem, okay? So if if you have splittings, you will cause if you have anisotropy, you will cause a splitting between these two phases. But most of the case, the SS waves, we only can see it very clearly at low frequency, at 20 seconds, something like that. So when you filter that, okay, so what you get is an apparent splitting between the radial and the transverse component. So, and you have to consider this if you try to use SS to measure the seismic anisotropy beneath the seafloor. So, what really you needed to do is not 2 matrices this time. You need a bunch of metrics, and if you have the earthquake, you need to consider the if you use deep earthquakes, and we assume beneath certain 500 kilometers, there's no seismic anisotropy. So for this part of the ray path, you can assume this is isotropic, and then you will, okay, so the anisotropy beneath the bouncing point is what you want to measure. So you would, the polarization direction first is modified by the anisotropy operator from the incident wave, and then you need to actually modify by a reverberation operators, and then you go by the splitting operator again, and then finally you have the receiver side splitting operators. So only after you collect these things, you can collect the splittings beneath the deflection point. And this is not easy. And what I'm showing here is the examples which I go through these processes. And I choose deep earthquake in South America recorded in Australia. And this CTAO station is a GSM station, and a lot of people may be familiar with that. That's actually, with the SKS data, you don't have so much, it really is almost isotropic. So you don't see any splitting at these stations. So you don't have the receiver side operators. So only thing you need to do is to collect the reverberation operators. Then you can measure these splittings from this data. So collected the radial component. And this is, I think, the same data, I think maybe different than I remember, I forgot, is South America deep earthquake recorded at CTL. So you can see the measured directions, fast direction, is at least consistent with the SKS measurement. And also, we tried some stations, the Tonga deep earthquakes recorded in the Kapawa array in South Africa, and this is also consistent. So this is India oceans, and then you see the actual splitting directions is consistent with the Mantle flows from dynamic numerical modelings. So this is kind of examples beyond SKS. If we have good data, and if you do careful enough job, you can recover the anisotropy beneath the seafloors, and you can testify whether there's strong channel flow or the mantle is reading the mantle wind beneath the beneath.
Could you do the same thing by looking at bounces off the bottom of the lithosphere boundary to compare what the seismology anisotropy is to the lithosphere anisotropy?
In principle, you can, but the bouncing from the lithosphere boundary is already very weak. So if you see a very clear reflection from the asthenosphere, lithosphere boundary, it's already a very good studies. But I think in principle you can. And I would show some examples which using receiver functions to determine crust seismic anisotropy, which was generally believed impossible from before, but with more and more good data, I think it's kind of timing you can do that.
Just going back to Dave's talk, you can imagine if you could do that type of thing, that you could address the question that he was talking about whether Africa is moving away from in reference, whatever reference frame you wanted to look at. You could try to find the thing that was stationary in the Mantle reference frame by finding low anisotropy in these hemispheres.
That's true. That's yeah.
Sounds kind of ambitious, but
Yeah, I will show some sort of array data. Maybe with more and more array data available, you can actually do this kind of things. And this, I think, so the young seismologist can do that.
So that's a research problem.
So I will, the last, I think, 20 minutes, I will go through the crust anisotropy, and I probably can finish earlier. I have.
Okay, so before you do that, I had a question. When one says you take the derivative of the pulse, how many people know what that means?
Well, everybody knows.
I can't see this.
You will take a derivative of the SB component, zero component.
Yeah, so how many people don't know what the derivative of the pulse means? Okay, sorry.
Good. Oh, good.
Well, this is important because it's diagnostic. And this is something that signal processors learn to do intuitively. So if we have, let's say we have a function that, I'm going to get points on my teaching evaluation for multi-use of visualization techniques. Okay, so let's say we have this function. So it's 0, and then it has a slope, some slope, and it has, that goes up to 1, and it's 1 again. So what is if we plot the derivative of that function, what does it look like? So what's the slope here? 0. So you go up to here at 0. And what's the slope here? Some value. And then what's the slope here? That's 0 again. Okay, so if you took the derivative of that function, it would look like that. Now let's take this function and let's turn it into this function. What's the derivative of that function? Pardon?
Delta function.
Okay, so how many people know what a delta function is? A few more people. How many don't know what a delta function is? And don't be ashamed, you know, it's not a reflection on your moral character. What a delta function is. Well, okay, so here the slope's 0, and here the slope's infinite, right? And here the slope's 0 again. So you would plot the derivative of this function is this function. Okay, so now let's take the derivative of that function. So the slope on this side is
0.
no. Well, out here it's 0, and then you come up here when it's positive infinity. And what's the slope on the other side?
Negative.
Yeah, so you take this thing and you turn it into something that looks like that. And you keep doing this, of course, then you get this, and so on. And actually, so this is a differentiation operator. Actually, it's a negative of a differentiation operator. But you can generalize this to any function at all. So let's suppose we have a function that looks like this. Here the slope's 0. Here the slope's positive. What's the slope right there?
0.
0. What's the slope here?
Negative.
Okay, so you start off with something positive. And when you get to the top, it has to go through 0, and then it has a negative slope, and it goes back to 0. So this pulse is something that you see frequently in these diagrams, and its derivative looks like this. So you start off with something that has 1 lobe, and you end up with something that has 2 lobes. You start off with 2 lobes, you end up with 3 lobes. And so on. And frequently you'll see a phase reversal as well. So can you show an example of that?
Yeah.
Yeah. So like here, this pulse is, the slope is 0, and that's positive, and that's 0, and that's negative. And over here you see it's positive, and it goes through 0 right in the middle, and then it's negative again. So that's all that means. So now you guys are hotshot signal processors.
So, but then can you remind us why it's useful?
Well, well, it's fun for its own sake. So if the radial component is equal to W of T, cosine 2 phi, where this is the azimuth angle, and this would be this shape, then what Fenglin showed was that actually this is the fast direction, right? This is F. Then the slow direction is equal to W prime of T.
Okay, transverse. Yeah, this is transverse.
This is transverse and this is radial. Okay, so that's right. So to see if something's actually anisotropic, it's not just is there a delay between these two phases, but is one of the phases rearranged. So that's why it's useful.
And also, basically, so if you have a map view of the earthquake and the stations and the waves coming from these directions, and in principle, the waves we are saying in a simple isotropic media, you will have the wave will be all the motion will in these directions. But like the example I showed you is that you also have some sort of this kind of motions. And so to generate this kind of energy in the transverse component, you can have anisotropy, and also you can have some sort of scattering like these things. That can also generate energy in this component. And to diagnostic whether this energy is generated from seismic anisotropy or kind of scattering is using this criteria. Okay, so now can you see this is the derivative of this?
The correct answer is yes.
Okay, so as I showed in like a NASA Savage's diagram, the crust anisotropy is thought to be less than 0.3 seconds, right? This is true. Actually, if you're using local earthquakes, like in Japan, you have subductions, you have station right beneath the earthquakes. You can using the earthquake have varied depths and try to measure the splittings and anisotropy in different range. So you can see that actually from those local earthquakes, what you get there is the faster dilation aligns the dilation of the maximum horizontal compressional stress. And the delay time is really small, from 0.03 to 0.2 seconds. So this means actually the source region is within the upper 15 kilometers of the crust, and the cause of the seismic anisotropy is probably the orientation of the crust, because if you have a maximum stress in these directions, the crust parallel to that this direction, compression direction, will open, and the perpendicular to this direction is closed. And then if you shear like this one, it's harder to shear, velocity is fast, and if you shear like this, it's easy, so the velocity is slow. Now, and there are some studies, I think a few studies using receiver functions which use the same sort of as the SKS. And what they found is the phi is actually the faster direction in this case is parallel to the direction of the maximum horizontal tensile stress. So which in this case suggests that the mechanism for the seismic anisotropy is due to the alignment of the minerals, and the delta T could be between 0.2 to 0.7 seconds. This is one study did in Japan where the crust is probably only 40 kilometers most case, in the worst case. But the real problem is when you're using receiver functions is the signal to noise ratios. We know the P2S conversion at the MOHO, the energy is only 10%, less than 10%, as George said the other day, 10% than the P waves. And then, so that's in the radio component. And if you so then the transverse component, you really get a much more weak signals, and you cannot use the SKS approach, the single event approach, to measure the seismic anisotropy from this P2S converted phase. So, okay, so this is the figure shows the P2S conversions. The phase we will use is basically a primary P waves incident to the MOHO and converted it to S waves at the MOHOs. And you see this is a very small signals, and it's about 5 to 8 or second after the P wave. So you need to have a very good data to do that if you only use a single earthquake. But you can use, actually, this is the same synthetic seismogram can show. If you have a lot of data, you can use the stacked method. Okay, so to do this, first thing you will see a variation roughly in the radial component, and in the transverse component, you will see a polarity switch, two polarity switch between the different back azimuths. So this is the vertical axis is the directions which the wave arrives. So I think we tested the single event method like the SKS. You try to minimize the energy in the transverse point for single earthquakes coming from certain directions. When you don't have noise, you get really nice assumed direction. In this case is the north-south. But if you have 30% noise levels, you started to get something off from the imported directions, when you have 60% of noise, actually you really don't know what you are measuring. And even if another thing is, as I said, when the moho is tilting, you can generate certain energy in the transverse component, which is sometimes is harder to tell from, is mixed in the seismic anisotropy. Even I don't give any anisotropy, you can still get some measurement from the data if the moho is tilted. So it seems actually the single event method is not appropriate for measure receiver functions. What you can do is adding a lot of stacking the data. So we can actually receiver function, if you stacking them, actually receiver function is even better than the SKS waves. The SKS wave, if the actual different event have different waveforms, you cannot stack different aspects, right? Waveforms as SKS. So you need to be down one aspect, then you need. But for receiver functions, the source signature is already removed. What left is the Green's function, which should be expected to be similar in all kind of directions. So you can do is, so we designed 3 different stacking methods to try to get a robust measurement. Is first you do the collection of the two phi contributions. You do the variation of the two phi's, and if you assume the phi and assume the delay times, and you collect this, and then you divide it by the original stacking amplitude. And also you can take the close correlation between, in this case, it's not the radial or fast or slow directions between different receiver functions. And you can also try to minimize the energy in the transverse component. And then finally, you can even combine them to see whether the measurement is robust. I think this is a synthetic test with no basically noise, and you basically can, all the methods give you the right same answers and catch the imported seismic anisotropies. Now, and if we apply the real data, it's really still harder to tell actually the mix between the dipping and the seismic anisotropy. So we designed a diagnostic test whether basically whether your measurement is robust or not. Basically, it's based on the classical signal to noise series coherent. For coherent signals, if you add them, the signal to noise ratio will increase with the effect of the number of square root and the number of you stacked. So we try to test 6 different cases. So remember, if you have seismic anisotropy, then you have the energy in this receiver time window is a signal, but they are not in phase. So when you add them, they will not coherent stacking. So the signal to noise ratio will not increase. But if we correct this polarity, we change the polarity and add them together, they should be coherent signal. They should increase with the number of the square root of the number of stacking. That's one thing we wanted to test, whether the energy in this component is simply a signal, coherent signal, or whether this is simply a noise. Okay, another thing, if we didn't change the polarity, we simply add them together, then the signal to noise ratio, the increase shouldn't as fast as after the correction of the polarity. And finally, after you correct the seismic anisotropy, there should be no coherent signal in the transverse component. So no matter how many times you stack them, the signal to noise ratio should be lower. And also for the radial component, we, after the collections, you should get a high signal to noise ratio for the P to S converted phase. So that's a small, like a diagnostic test we did for try to see how robust the seismic anisotropy is showing the data. So this is again from synthetic data with 60% of noise, and you can see all the open circles or open symbols is the summation or before the correction of the anisotropies. And the circle is with a polarity change, so you can see it's increase with the number of the stacking. And after the corrections, which shown in the solid symbols, there's no signal in the data. So this, whatever, how many times you stack, they should be flat. And in this part showing is the radial component. If you correct the seismic anisotropy, they are more coherent. So if you add them, so the signal to noise ratio increase much faster than if you didn't correct this small delay time in the data. So that seems to a diagnostic test. So we did this actually for an isotropic model, which it works, which I showed you in the before. And we also tested this for isotropic model, but with dipping moholes. And you can see, if you using the 4 different ways, you can see sort of seismic anisotropy with some splitting times. But when you do the signal to noise test, you cannot see the same feature which I explained in the previous slide. And also we found the ratios, the individual ratios after the collection and before collection tended to be lower compared to the one which we showed before. After the collection, the ratio is much higher than the before the collection. So basically we try to use this method to the real data. And the area we select is the southeastern margin of the Tibetan Plateau. This is the areas. And so, the crust in this area is actually, we just use the same receiver function data to map out the crust thickness. And the crust thickness this is the Yunnan and the Tibetan Plateau, and this is Sichuan Basin here. And the crust in the southwestern Yunnan is quite thin, from 30 kilometers, and the part of the plateau is basically could go to 70 kilometers. Now there's models, different type of models has been proposed for the deformations, the lithosphere deformations in these areas. So this is basically Paul's group. They favor to basically vertical coherent deformation in these areas. In other words, the deformation inside the crust is similar to the mantle lithosphere. And the MIT group, they actually favor kind of low cluster model. So in this case, you will expect a large anisotropy maybe in the crust. And then the lithospheric mantle may not necessarily be deformed as similarly as the up crust, the surface deformations. So we wanted to, so in this place, knowing how much seismic anisotropy in the crust is very important. And so this is the MIT group. They actually put a Pascal array, and this is the SKS measurement, the data. So again, the faster direction, they only show the directions, and you see actually along the 30 degrees, for some reason the faster direction is east to west, and then goes to like south-north, and then at this dashed line, south to this dashed line, everything tend to orient east-west.
And the red arrows are GPS.
And the red arrows is the GPS measurement, and that's kind of rotation in the around the syntax. Okay. And they, since the Pascal they only deployed like I think 18 or 2 years, so there's not enough data to cover the whole backchasm. So this is kind of measurement from individual earthquakes. Now, we got data from the permanent seismic network in China, regional network in China. The data we have is from July 2007 to July last year. We have 3 years data, and we have about 88 stations in the study areas. And so we applied, well, before that, I think I needed to show you the individual receiver functions. This is one station which has a very good backchasm coverage, and most of the stations have the similar kind of backchasm coverage. And again, the waveform is plotted as a function of backchasms from 0 to north to actually 350, and then this, and everything is aligned at the P waves. And these are the individual waveforms, and this dot are the expected arrival time from an isotropic velocity medium, and you see some sort of variations. And if you add them with every 10 degrees, you add those receiver functions, so that actually clean up a lot of the noise. And if you plot the similar ways, you can see some sort of variations. For example, in this case, you see something arrived earlier, and here is late, and something earlier again in this area. So you see some sort of variations. And if you were apply the same techniques to that, you have different three individual stacking method, and all shows the same sort of directions, and with slightly different amplitude of spreadings. And we see actually we actually try to use the synthetic test. This time I'm using the square to plot the collection, the stacking after the collection of the plurality, and this. So you can see this from this diagram. We see this measurement is robust. Another measurement from a station in the Tibetan Plateau, you see actually the signal to noise increase with the stacking numbers for the T component with the plurality collections, and also you see actually the radial component aligns better than after the collections, and the amplitude of the ratio is high, so indication that there's seismic anisotropy there. And after we go all the stations, we only got like 26 measurement. Shown here is the faster direction is shown as the line is showing the faster direction, and the symbol shows the splitting times. And overall, you see actually a large splitting time, although the directions in some direction changes quite a lot. But overall, you see the splitting time actually is larger from the station in the plateau than actually in the Yunnan, where you have synchrony. You almost see no splitting there. And if you plot the splitting time as the S minus P travel time, basically the S wave travel time is this number time 2.2 is the S wave travel time in the crust. So you see roughly see a linear increase with the S wave travel time, and the amplitude is, some of them can even go 0.29 seconds, and the SKS is 1 and 1 point, in this area is, I think it's less than 1.5 seconds, I think. And if you compare to the Crustal anisotropy and the SKS measurement, it seems the direction kind of, most are agrees, but some does not agree. So this is 30. So this is 30 and 25, and the 25 is here. And we definitely did not see this actually, the sharp transition from north-south to east-west in this around the 26. So, and we actually, all the station cross the contribution from the station in the Yunnan province is really negligible. So all this measure, what's really this measures is the mantle deformation here.
And so the mantle deformation splitting would have to be much greater if the crustal component was almost a second perpendicular to what you see from the SKS, right?
Yeah.
So the mantle thing would be like...
No. In this case, actually, for Yunnan province, this is almost 0.2, 0.3, so it's kind of negligible. Yeah. Yes, very small circles. Yeah. Okay, so I really don't think. Okay, so. Okay. I will go one a few. So what can we do for the future? I'm really not expert in doing seismic anisotropy, but since we have a lot of array now data available in the world, so we can using kind of LIDAR method. So one method we can using is the SCS reverberations, vertical reflection from the core mantle boundaries, and you can compare different array paths, so you can actually resolve the anisotropy in different regions. And so this is kind of example of the SCS and splittings. And for example, this is the Japanese did with the HiNet. They can see this is 150 degrees is the volcanic front. I think this side is measured the mantle wedge is kind of parallel to the subduction and converted to the perpendicular. So those kind of seismic anisotropy. So you have 3 earthquakes. You can actually map out all these anisotropies in different areas. And lastly, I will show actually which the data I don't think I understand. This is a small array. I put it actually more than 10 years. The Kimberley array by the MIT and the Carnegie group. And this is only like 70 kilometers, okay? So you see the splitting time changes from 0.75 second to 0.2 second. So remember, the waves is not it's not a noodle, right? It's actually a pipe. The Fresnel zone is in the upper mantle is even bigger than the array size. So why you have so much variations, right? This is simply showing the seismogram radial component and the distance. This is earthquake from Indonesia. This is only like 70 kilometers, 70. And you see strong SKS in the northeast stations and gradually decrease to 0. And at the beginning I saw it's maybe due to some funny structure in the core mantle boundary. But this is actually, it's definitely caused by splitting because the derivative relationship. So I think with more and more data, you can find more and more detail of anisotropies in the different depths and around the world. Okay, so I don't think I will stop here.
Questions?
So about the receiver functions, how can you distinguish between anisotropy at the interface and that causes the conversion and between the interface and the surface?
What do you mean interface?
Is it localized to the point at which the B converts to the S that you get the anisotropy cause, or is it?
Or you mean
during the path of the S?
Whether this is due to a localized area in certain depths or it's distributed the whole crust? Is that the question you want?
Yeah.
Well, this, you know that you have to compare then the local earthquake data and the receiver function data to try to separate them. But as I said, they are measuring different types of anisotropy. One is kind of more crack related, another is kind of more mineral alignment related anisotropy. And they actually have very different, the waves you used have very different frequencies. You know, I'm not sure whether you even can compare. I didn't mention anything about the frequency dependence there, because